Hi class, in this recording we are going to continue diving in through chemistry. So let's have at it. As we're looking at these chemical concepts, we need to talk about molecules versus compounds. So when we think of a molecule is going to have two or more atoms united by a covalent bond. Now a key distinction here is we can have two atoms of the same element or two atoms of different elements. We can still have molecules. Molecule is a rather inclusive term. That just refers to the number of atoms, not the number of elements. When we think of a chemical compounds have two or more different elements. So when we think of hydrogen, H2, it's a molecule, but it's not a compound because it has only one element, two hydrogen atoms. But when we think of H2O, water, it is a molecule because it's more than one atom, and it is a compound because it has more than one element present in it. As we look at molecular formulas, a molecular formula tells the specific number of elements and atoms of each element present in every compound. So as we look at this C6H12O6, this is saying that we have 6 carbon atoms, and then we have, lost it here, let me try again. There we go, 12 hydrogens and 6 oxygens present in that particular molecule. When we think of mixtures, mixtures need to be physically blended. So for instance, if we have just water, water by itself is not a mixture because it has only one thing present in it. But if we take water and add sugar to it and stir it together, we're physically blending those things together and making a mixture. Note they are not being chemically combined. When we chemically combine something, we change the chemical and physical properties, particularly the chemical properties of that substance. Another way to think of a mixture is that you can physically combine it and physically separate it. So when we think of liquid in our body fluids, we have complex mixtures in our bodies. Most mixtures in our body are going to be dissolved in water. This is one of the reasons why we refer to water as a universal solvent. It's able to dissolve very many things, many different things, I should say. When we look at water, depending on our age and our body fat composition, it could be 1/2 to 3/4 of our overall body weight. So age, sex, and fat content, generally speaking, the more fat you have, the more water. Females will have more water than males, and young people will have more water in their bodies than old people. Oops, I went 2 slides there. Here we go. So as we're looking at water, water is referred to a universal solvent because it's able to dissolve so many different chemicals. It has a high solvency. Water is able to dissolve many chemical compounds that are hydrophilic. They dissolve in water readily. Since water is a polar molecule, it has a polar covalent bond. Molecules that are dissolved in water also need to be polarized or charged. So sugar molecules, ionic compounds are able to be dissolved, ions, electrolytes, all these different things are easily dissolved in water. Things that are not easily dissolved in water, that do not dissolve in water well, are referred to as hydrophobic. And because water is polar, things that don't dissolve in water are typically nonpolar or neutrally charged. The phrase that I remember my Gen Chem 2 prof taught me was like dissolves like. Polar solvents dissolve polar chemicals. Nonpolar solvents dissolve nonpolar chemicals. As we look at the metabolic reactions, the chemical reactions that keep us alive, they all depend on how easily we can dissolve our favorite chemical within water, the chemicals that we need to stay alive. So as we look at water and mixtures, water is able to dissolve ionic molecules by overpowering the ionic bonds within the ionic molecules. As we look at sodium chloride being dissolved in water, let me move this up over here out of the way. We can see that we have a sodium ion right here, and the sodium ion has a positive charge, and the oxygens, which have partial negative charges, are facing that sodium ion. in rings around the sodium ion. This is referred to as a a hydration sphere around that ion. And this is a two-dimensional picture trying to represent a three-dimensional phenomenon. When we look at chloride, chloride has a negative charge, and the partial positive hydrogens of the water are going to be attracted to that negative chloride to form another hydration sphere. When we dissolve chemical compounds in a liquid, we make a solution, and we just need to cover this terminology to make sure that we're all on the same page. So as we look at solutions, a solution is going to have two primary things in it. It's going to have a solute and a solvent. The solute is going to be what we have less of, and then the solvent is what we have more of. That's the best definition I can give you right now. Almost always, our solvent of the human body is going to be water. Water is very commonly going to be used as the solvent, and most of the time, water is what we have the most of in a solution. And then the solute is typically what we have less of in the solution. Common examples of solutes include hydrogen ions, glucose molecules. Oh, excuse me. Oh, I should drink more coffee. Or pick your favorite ionic compound, any of the amino acids too. But something that is confusing for a lot of individuals is that the solute is not always a solid dissolved in water or the solvent. Instead, the solute can be a gas dissolved in the solvent or a liquid dissolved in the solvent. So the solute is what we have less of, the solvent is what we have more of, and combined they make a solution. If we have an aqueous solution, and we're just going to assume aqueous solutions between now and the end of human anatomy and physiology, and we have hydrogen ions in that aqueous solution, that's going to be an acidified solution. Acids donate protons or release hydrogen ions into that aqueous or water-based solution. Basic chemical compounds, when we think of acids and bases, are going to receive protons or remove protons from solution. As we think of bases, many of you are taught the Arrhenius definition of acids and bases, which depends on the hydroxide ion. As we look at this OH-, this hydroxide ion receives a hydrogen ion and removes it from solution. So whether you're using a Arrhenius definition or a Lewis definition, we're still going to work with this idea that bases remove protons, acids release protons into solutions. And as we look at pH, pH is going to be a measurement of the hydrogen ion concentration. The unit of concentration we use to measure hydrogen ions is molarity. And we're not going to be doing molarity calculations in this class. We just don't have time for it. But as we look at pH, and we're certainly not going to be doing pH calculations, as much as I would love to. But as we look at the pH, if the pH is exactly 7, we call that neutral. And at exactly 7 pH, the number of hydrogen ions, the concentration of hydrogen ions is equal to the concentration of hydroxide ions. If the pH is less than 7, it's an acid, and we have more protons than hydroxide ions. The concentration of hydrogen ions or protons is greater than hydroxide. And then if we have a pH above 7, it's a basic or alkaline solution. And that means that we have a higher concentration of hydroxides relative to hydrogen ions. Here's an example of common chemicals and where they fall on the pH scale. So exactly at 7, we have pure deionized distilled water. When we look at cleaning compounds, as a rule of thumb, cleaning compounds tend to be basic in nature, and they also are going to be slippery. As a good rule of thumb, if you wiggle your fingers on something and it's slippery, that liquid is probably going to be alkaline or basic. And then when we look at food products, a lot of the food that we eat, most of the food that we eat is going to fall into that acid range of the spectrum. And then as we look notably at our stomach is highly acidified. The hydrochloric acid, the 1 molar hydrochloric acid in our stomach has a pH of 0, but generally speaking, it's not going to be at that 1 molar concentration because we're constantly adding water and other chemical compounds like food to our stomach. So we dilute the hydrochloric acid and raise the pH typically from 0.9 to 3.0 within our stomach. That's all we have for this recording. If you have any questions, please feel free to post them on the class discussion board or shoot me an email. As always, happy studies.